Assalamu alaikum warahmatullah. Today we'll be discussing the wideband fading. Okay, the wideband fading occurs when the symbol duration is less than the delay spread. When this occurs, inter-symbol interference occurs, which leads to wideband fading. So now we have three synonyms, three equivalent concepts or expressions. First, frequency selective fading, and inter-symbol interference, and the big topic, which is wideband fading. So those three concepts are equivalent in some sense. Okay, so when we have inter-symbol interference, meaning that the symbol duration is much less than the delay spread of the channel, so the delay spread is related to the wireless channel. Okay, in this case we have multiple copies due to multipath arriving at the receiver, and we can resolve them, we can distinguish them from each other. In a general sense, let's say that we have two paths only, so we can write the expression for the received signal as equation 49 here. So we have the first copy and the second copy. The first copy suffers attenuation A sub 1, whereas the second one suffers from A sub 2 attenuation, and it goes through delay tau 1 here and tau 2 there, and now here we have let's say phi 1, which is the phase shift due to the first path, and the phi 2. Okay, so of course the delay depends on the distance traveled in each path. So usually the strongest path is the shortest path, because we have less distance covered, meaning that we have less power lost. Okay, so we can describe it as a convolution with an channel impulse response having two components. Okay, so this means that I have two paths. Okay, the first component will result in a attenuation of A sub 1 and delay tau sub 1. Similarly, the second path, as we said earlier, will cause an attenuation of A sub 2 and a delay of tau sub 2. Okay, so we can take the Fourier transform of this channel impulse response, will give us the channel frequency response here. So we have again two components, which are now two complex exponentials. Now if we investigate or look into the magnitude of the channel's frequency response, easily we can take the magnitude, then we can take the first component as a common factor leading to this. Now we recall that the magnitude of any complex exponential equals to 1, right? So we are left with this expression in equation 53. Now this value will reach its minimum point when f, the frequency, equals 1 over 2 delta tau, okay, which is called the notch frequency. Why it's called the notch frequency? Because it will be like notching the frequency response and leading to a dip in it. So this is an example here. We have this impulse response of a WCDMA, which is a 3G system channel. We have the bandwidth of 5 megahertz, right? And we have, you can see here that the delay is in the order of nanoseconds. So the first delay is half a nanosecond, the second delay, sorry, microseconds. So this is microseconds, right? Microseconds. So the first delay is half a microsecond, whereas the second delay is 1 microsecond. See now, we have delay speed of 0.5 microsecond, right? So clearly we can expect to have two symbols arriving at the receiver, which we can distinguish from each other. And now here, as you can see, at this point, at this frequency, which is 1 megahertz, right, which is actually less than the bandwidth of the system, we have a dip in the frequency, meaning that, let's say, if we draw the bandwidth, which is something like this, right, it will be something like this. Sorry, this is strange. Something like this. So this is a 5 megahertz bandwidth. This part of the signal will suffer attenuation, which leads to degradation in the performance. Okay, we can now summarize. Sorry. Here. Now, if the bandwidth of the system or the symbol is very small with respect to the delay spread symbols, this will lead to the previous fading that we studied, which is called flat fading or narrowband fading. On the other hand, if the band is very large with respect to the delay spread, we will have wideband fading, as we said earlier.